In the last video, we just finished with the comparison of two area system and single area system subjected to a disturbance. Now, whenever it is two areas subjected to a load disturbance, we are left out with the final mathematical model that has to be drawn. We'll see that now. So this is the final two area model. You very well know the expression which you have seen in the previous video. Delta omega is equal to minus delta PL1 by beta 1 plus beta 2. This is nothing but the final expression for response to the load disturbance in a two area system. I have mentioned here, it has been explained in the previous session. So now we have drawn the block diagram for that. So this part of the block diagram, what you can see here, corresponds to the single area system. This corresponds to another single area system. Since you are operating two control areas connected by a tie line, the overall block diagram gets clubbed, and in between you are having an integrator here which is going to supply tie line power. What you will have to observe here is the tie line power near the area 2 happens to be positive, and which when fed to area 1 is negative. That means if tie line power is positive, that means the power is going out of this area, and here if it is negative, the power is being received by this area. So you already know that during the disturbance I already explained that the power flows from area 2 to area 1. So power is flowing out from area 2, so positive sign here, and power goes into area 1, so negative sign over here. So both the diagrams have been clubbed. Along with that, we are able to see delta P12, which is tie line power flow. So we are supposed to stop at this particular stage. Next, I'll move to the next topic. Now we have a problem on two area system. First, I would like to read the statement. A two area system connected by a tie line has following parameters on 1000 MVA base. R1 is 4.5%, B1 is 0.6, H1 is 5, R2 is 6%, B2 is 0.85, H2 is 4.5. The units are running in parallel at a frequency of 50 Hz. The synchronizing power coefficient is 1.9 per unit at initial operating angle. A load change of 150 MW occurs in area 1. Determine the new steady state frequency and change in tie line power flow. Also compute the change in mechanical power in response to the disturbance. So again, this is a two area system. You are having control area 1, control area 2 connected by a tie line. Whatever topic you have seen in the previous session, this problem is based on that. So what is happening here is, coming to area 1, the regulation is 4.5%, and frequency regulation constant is 0.6, inertia constant is 5. Similarly, R2, B2 and H2. Units are running in parallel at a common frequency of 50 Hz. Synchronizing power coefficient is 1.9 per unit at initial operating angle. So later on I'll tell you what is synchronizing power coefficient, which is denoted by PS. Now here, a load change of 150 MW occurs in area 1. There is an increase in demand by 150 MW in area 1. So whenever there is an increase in the demand, obviously there will be a drop in frequency. We are supposed to find that new operating frequency. Determine new steady state frequency and change in tie line power flow. Since it is two areas involved, whenever there is an increase in load demand in area 1, there will be a drop in frequency in both the areas. So to meet the shortage of power generation in area 1, power flows from area 2 to area 1. What amount of power is flowing from area 2 to area 1 has to be found, which is tie line power flow. Also compute change in mechanical power in response to disturbance. That is, the individual share by both the areas has to be found. So first step is, we'll be using the formulas for finding the change in frequency. See, I have written delta omega is equal to minus delta PL1 by beta 1 plus beta 2. This was derived in the previous session. So always remember, frequency and speed are interchangeable parameters. In place of frequency, I can write speed, or in place of speed, I can write frequency, because they are directly proportional. So even if you write delta F here, it does not make any difference. So delta PL is nothing but the change in load demand. First, I would like to convert it into per unit. So here you can see it is 150 MW is the change, and the base value happens to be 1000 MVA. So 150 divided by 1000 will give you 0.15 per unit. And beta 1, you know, by formula it is B1 plus 1 by R1. B1 is given as 0.6, R1 is given as 4.5%, which is 0.045. You will be getting 22.82. Similarly, I will be calculating beta 2 for the second machine. Further, minus delta PL1 by beta 1 plus beta 2. Once I have calculated delta PL1, beta 1, beta 2 in per unit, I'll be using it in the formula for delta omega. So delta omega will be minus 0.0037 per unit. I'm interested in converting this into actual quantity. Since this is speed or frequency, the standard value or nominal value is 50. If I multiply it with 50, I'll be getting 0.185 Hertz. So there is an increase in load demand by 150 megawatt. So there is a drop in frequency by 0.185 Hertz. So since it has reduced by 0.185 Hertz, the new value of frequency is 50 minus 0.185, which is 49.815 Hertz. This is the first part of the problem. Next, I need to find the power that is flowing from area 2 to area 1 during this disturbance. So the formula for that is minus beta 2 into delta PL1 by beta 1 plus beta 2. Already we know that minus delta PL1 by beta 1 plus beta 2 itself is delta omega. So we just have to multiply beta 2 into delta F or delta omega. So here 17.51, it is in per unit. Delta F also I'll take it in per unit. I'll be getting 0.0648 per unit. If I need the actual quantity, I have to multiply it with base value, which is 1000 MVA is the base value. You'll be getting 64.8 megawatt. So whenever there is a disturbance in the system, that is increase in the load demand by 150 megawatt in area 1, 64.8 megawatt is transferred from area 2 to area 1. Next, we'll have to calculate change in mechanical power in both the machines. In the first machine, which is in area 1, we already know the formula for regulation. We are using the same here. Delta F by R1. Delta F is 0.0037 by R1 0.045. I'll be getting 0.082 per unit. Since it is power, to get the actual value, the base value 1000 is multiplied and we get 82 megawatt. Similarly, we have delta P2 0.067617 per unit, which is 61.7 megawatts. So this finishes the problem with the two area system. Next, we'll move to the last topic of module 3. Frequency bias tie line control. See, similar to what we did in single area system. See, in single area system, initially we studied about steady state response, and then we came to know that since the speed used to settle after some oscillations, we thought to produce the reference power automatically by feedback. There also we have done that is where we introduced the secondary ALFC loop. Initially it contained primary loop, then we created secondary loop such that the reference power was also generated automatically. Same thing now we are doing for two area system. Initially we studied the steady state response for a two area system in the previous topic. Now we are trying to generate the reference power through feedback by including another loop. That is what is frequency bias tie line control. So to repeat the concept once again, you are having control area 1, control area 2. There is an increase in the demand in control area 1. Since there is an increase in the demand, there is a drop in frequency. Since both the systems are interconnected, frequency drop will be there in both the areas. Now there is a insufficient generation in area 1 because the demand has increased. To meet that demand, the generation will be partly increased in area 1 and remaining will flow from control area 2 to control area 1. That is nothing but your tie line power flow delta P12. Now, as I told you, for quicker response of this particular operation during the disturbance, we need to include secondary loop along with integrator. We'll be using an integrator block so that the reference is generated by feedback. So just try to compare the previous block diagram with this block diagram. You can see this is the block diagram for area 1 and this is the block diagram for area 2. The only difference between this diagram and the previous diagram is your reference power is getting generated through an integrator, and that is nothing but area control error ACE. ACE is given by B1 delta omega 1 plus delta P12. So you can see delta P12 comes from this point and delta omega 1 into B1 comes here. So delta P12 and B1 delta omega 1 gets added and the resultant is ACE1, area control error, which when fed through an integrator will generate the reference power. Same thing happens to the second system also. Tie line power is flowing from this particular side and here you are having B2 and you are having delta omega 2. This is delta omega 1, this is delta omega 2. Delta omega 2 into B2 is getting is coming to the summation here, and here you are having tie line power. If you take the algebraic sum of both through an integrator, the reference will be generated. Now the reference power also is getting generated through the system feedback itself, and we are not manually supplying it. So because of this, during the disturbance, the response of the system will be quicker. So for you to just recollect, I'll show you the previous block diagram without this so that you can understand. See, in the previous case, you can see delta P12 is just fed to area 2 and area 1 over here. Tie line power flow exchange is happening, but there is no feedback. Delta P1 reference is given manually. Delta P2 reference is also given manually. But now we have generated this automatically through an integrator. Now I'll come back to the actual diagram. So now you can see the difference. Here delta P12 is fed back here. B1 delta omega 1 plus delta P12 is generating error, and reference power is being generated. That's the difference between previous case and this case. So with this, I'm concluding module number 3. Next, in the next video, I'll be starting with module number 4. So please go through all the expressions. A lot of concepts are involved here, and mathematical derivations are there. So practice them once. In case you're having any doubts, anytime you can give me a call and clarify.